Okay, in the second 4.1 video, we're going to look at a couple of transformations on exponential functions, and we're going to identify the domain, range, and asymptotes for those. For this first one, I've kind of taken over the whole page for example 3a. We have the function f of x equals 3 to the x plus 1 minus 2. So what I've done is I've actually already done the computations. I've taken these x values here, substituted them into the function, and got my resulting function values, okay, my y values. So what I'm going to do is I'm going to plot these points on the graph so we can see what it looks like. So now we get some fraction answers, and just know that we have to be as precise as we can, but know that we might not be perfect 100% accurate. I'm going to plot this in blue. I'm going to start with 0, 1. That is my first coordinate that I want to plot. Okay. Then I have -1, -1, which should be right here approximately. Then I have -2, -5/3, so that's like -1 2/3. So it's like right there. Okay. Then I have 1, 7, so 1, 2, 3, 4, 5, 6, 7. And then 225, which goes off my page. If you notice, the value that we're going to get extraordinarily close to and never hit, I'll plot that in green, is this right here. Now it's going to be really hard for me to draw that, where it's not going to touch, but I'm going to try my best. Okay, pretend like those did not touch. So you can see here that the domain is still -infinity to infinity. Okay, it's going on forever and ever in both x directions, both towards -x and in the positive direction as well. Now the range, because it shifted down, this -2 shifted the whole function down by 2, the range would go from -2 to infinity. So it starts at -2 and goes up. Those are my y values, that's my range. Okay, and then our asymptote that I plotted in green is going to be equal y equals -2. So that downward shift of 2 affected our range and it affected our horizontal asymptote. For the second example, again, we're going to graph the function. So this is for 3b, g of x equals -3/4 x plus 4. I just want to acknowledge right now that this plus 4, we already kind of have an idea what it's going to do. It's going to shift our asymptote from 0 up to y equals 4. So I can actually draw that in right now. 1, 2, 3, 4. That's like right here. Lovely. Okay, so we have that vertical shift upwards. We also are going to have this reflection. We get a reflection over the x-axis because the exponent does not apply to that negative sign. So every single one of our values is going to be negative, and then we add to it plus 4. So we're going to get some positive values, and the ones that I checked here actually give us all positive values. We can see the general pattern of what's happening. So let me plot the points. Again, I just calculated each value by substituting in my x values into the function and getting the corresponding y values. So when I substituted in, let's start with 0, I got 3. So 0, 3 is right here. No, it's not. Close enough. Okay, and then 1 and 3 1/4, so we're getting closer. We are getting closer to that horizontal asymptote, because then it gets up to 3 7/16. That's fun. At -1, we get 2.6 repeating, or 2 2/3, so that's going to be somewhere up there. We get 2.2, and then we get 1.63. So we get the sense that it's getting further away from the asymptote. It's going to look something like this. Okay, so we have that reflection over the x-axis and then an upward shift of 4. Now my domain is still negative infinity to infinity. It goes on in both directions for all values of x. The range starts from negative infinity because this is going downwards forever. The range starts from negative infinity and goes all the way up until we reach that asymptote, but not including that value. So it's going to go from negative infinity to 4, not including 4. So make sure that this is a parenthesis and not a bracket. Okay? Then our asymptote, which I drew in red, so I'm going to write in red, is going to equal y equals 4. This next part is the fun part when it comes to exponential functions. We're going to take a look at some applications of exponential functions. So first off, when we want to evaluate the exponential function with the base e is a special number. Honestly, if you look at the media from my math lab that I posted, it's like lesson 4.1 exponential functions media. There's actually a really cool math talk, and they talk about the number e, and they talk about applications, and it was actually really interesting. I watched all 3 of them. So if you have some time, go ahead and watch those math talk videos, and you'll learn a little bit more about e. But you really want to know, what we really want to know about e is that e is a universal constant, and it is an irrational number, and it's kind of known as the growth constant and the growth coefficient. So growth and decay. So one thing to note is that E is a number. There is a button on your calculator that is labeled E, and they're not talking about the letter, they're talking about the number. And we can actually calculate with the number E. So for these first 2, we can evaluate E, and we're going to round to 4 decimal places. We just use our scientific calculator, type E to the second, and we're going to round this once we get our result to 7.3891. Now, I'm actually going to change that symbol from the equal symbol to its approximate because we rounded it. It's rounded and cut off a huge chunk of it. So we want to make sure we're using approximately and not equals to. Now on this one, this is 15e to the negative 3. Again, we can input that in our scientific calculator and we get 0.7468 when we round. Okay, so e is just a number. We can use it for calculations. It's going to be really important when we start looking at applications. Does anybody have a bank account? Does anybody have a savings account where you earn interest on your savings? Does anybody have a credit card where they apply interest on how much you owe them? So any of those actually uses exponential functions to compute the compound interest. So P is the principal, the dollars in principal that is invested or borrowed at an annual interest rate, R, for T years. Then we have these 2 formulas that we use to figure out how much money or interest combined with the principal has accrued. Okay, so the first one is A equals P times 1 plus the rate divided by the in compounding periods to the compounding periods times T. I'm going to write that a little bit more clearly because the copy is not perfect. 1 plus R over N to the N T. So T is time in years, N is the number of compounding periods. So we're going to look at an example and talk about the different compounding periods. But the interest could be compounded monthly, it could be compounded annually, it could be compounded quarterly, it could be compounded semi-annually. And then the last one actually uses a completely different formula. So if something is compounded continuously, we use this formula instead. The amount A in dollars in the account after T years under continuous compounding would be equal to A equals P to the ERT. The principal times E to the rate times the time. Okay, and remember that that time is in years. So let's look at the first example. Suppose that $15,000 is invested with 2.5% interest under the following compounding options. Determine the amount in the account at the end of 7 years. So I'm going to label the information they gave us. This first amount here, that's my principal. This right here is my rate. The 7 years is my time. And then these are what's going to tell you what my N is. So compounded annually, that means once a year. That's going to be A equals 15,000 times 1 plus my rate. Now I need to change that percentage. Okay, I need to change that percentage to a decimal. So that's going to be 0.025 over the compounding periods is going to be once per year, and then 1 times 7. Okay, because that's the compounding periods once per year times 7 years. When we calculate that, use your scientific calculator to calculate this. You get $17,830.29. Please make sure that you round to the cent. Round to the nearest cent. Okay? So that's looking pretty nice. You put $15,000 in 7 years, you've earned a little, almost $3,000 more on that. That looks pretty cool. Let's see what happens if our interest is compounded quarterly. That means 4 times per year. That means that my N equals 4. So that's going to be A equals 15,000, my principal, times 1 plus the rate, 0.025 over the 4 times per year. And then with a power, or the exponent on that, is going to be 4 times 7. Again, we can calculate that in our scientific calculator, and we get $17,858.96. Notice that when this compounded 4 times a year instead of compounding once a year, we end up with more money. The reason why is because the money that you made the first time it was compounded actually gets money earned on that. And then at the next quarter, that whole amount gets money compounded on that, interest compounded on that. And so that should make sense that if it's compounded more frequently, that we get a higher value. Now, if something is compounded continuously, we use the other formula, the A equals P times E to the RT. So that's going to equal 15,000 times E to the 0.025 times the time in years. So when you calculate that in your calculator, you get $17,868.69. Okay? So just a couple of things to note. So the most money I could get is if something is compounded continuously. That is $10 more in this example, approximately $10 more than if it had been done quarterly, and it's about $38 more than if it had been compounded annually. So it doesn't seem like much, but over time or with higher interest rates, it's actually a lot of money. So, some other things to note is that something could be compounded semi-annually, which means that that is 2 times per year. Things can also be compounded monthly, which would be 12 times per year. Okay, and something could be done daily, I guess, technically, which would be 365 times per year. Okay, Now, most of the time, you probably won't see something like that. You're more likely to see monthly, semi-annually, quarterly, and annually, or something compounded continuously. So our first example involves money, interest. Our second example is going to involve half-lives. So we're going to use this exponential functions and applications. In this application, we have weapon-grade plutonium is composed of approximately 93% plutonium-239. The half-life of Pu-239 is 24,000 years. In a sample originally containing 0.5 kilograms, the amount left after T years is given by A of T equals 0.5 times 1/2 to the T divided by 24,000. It's a little bit hard to see, so I'm going to make sure we understand that those two things are being divided. Okay, so they tell us to evaluate the function for the given values of T and interpret the meaning in context. Okay, so this first one, we're going to substitute in our 24,000. So that's going to equal 0.5, which I'm just going to rewrite as 1/2 times 1/2 to the 24,000 divided by 24,000. Any number divided by itself is just 1. So that's going to be 1/2 times 1/2 to the 1, which is just going to end up being 1/4. 1/4, that's going to be in kilograms, right? 1/4 kilograms are left, which makes sense. If we're evaluating the function at 24,000 years, that is equal to the half-life of the plutonium. So if we started with 0.5 kilograms, after 24,000 years, we should only have half of that left. Half of half is 1/4. Okay, so hopefully that makes sense in context. Then for the next one, we end up with 1/2 times 1/2. I just keep rewriting the 0.5 as a 1/2. I just like it better that way. And then 72,000 divided by 24,000. I'm just substituting in that value into the function. That gives me 1/2 times 1/2 to the third. Okay, 1/2 to the third is 1/8. So that's going to equal 1/16. Now you could also plug this into a calculator. Okay, if you do that, you're going to get 0.0625, and that's just equal to 1/16. Okay, so that means that after 72,000 years, that's the time, remember, in years, after 72,000 years, only 1/16 kilograms of the Pu-239 remain. Okay, so in an application, you want to make sure you understand the computations you need to do, but also you need to be able to interpret the meaning of that result. So make sure you read and understand each word problem carefully so that you can interpret the meaning of your results within the context of the problem. All right, thank you. Good luck with your homework and let me know if you have any questions.